Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. Tonight, above your roof and mine, beyond the gentle hush of atmosphere, starlight continues its long, silent journey. Some of it began its voyage before Earth even had oceans. Some threads of light, older still, have crossed entire epochs of cosmic weather, slipping quietly through the deep time fabric of space. They arrived not with a bang, but with a whisper, settling on our lenses, our detectors, our waiting minds. And tonight, we turn our attention to something strange. An object came toward us recently, 3i Atlas. It glided from beyond our familiar planetary paths, dipping briefly into the warmth of our star's domain before fading again into the night. But here's the thing, it didn't stay long, it didn't veer close, and it didn't behave like a threat. Still, it caught attention, because it came from interstellar space, like a message in a bottle tossed from an unfamiliar shore. We look up, and we wonder, what is it really? Could it hurt us? Is this the thing we should be worrying about? But the cosmos rarely plays by the rules of our fears. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. Wherever you are tonight, on a couch, beneath a blanket, or curled under dim light, feel free to tell us your location and local time in the comments. We always love knowing where our fellow stargazers drift off. Now, dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. We often fear what we can see, a looming object, a fast-moving asteroid, a strange flicker across the sky. It's easy to assign danger to something dramatic, but in astronomy, that instinct can mislead. Often, it's the visible that is safest. The flashy visitor that announces itself may have no interest in staying. It's the quiet, the hidden, the undetectable that holds deeper uncertainty. 3 Atlas, like its predecessor, Oumuamua, is an interstellar object. That term alone carries weight. Something not from our solar system, but from another stellar neighbourhood entirely. It's rare. Only 3 such visitors have ever been confirmed. A cosmic tourist, wandering alone. It approached at over 26 kilometers per second, too fast for capture. Like a skipping stone, it dipped past the sun and continued outward. We had a brief window to watch it. Telescopes trained their gaze. Spectral analysis was done, and it turned out to be unremarkable in many ways. Ice, dust, perhaps a fractured comet body. Nothing that suggested threat. No erratic maneuvers, no bursts of radiation, no hidden payloads. In fact, as strange as it may sound, its trajectory tells us this object is harmless precisely because it's visible. It follows Newtonian paths, obeys gravity's curves, and reacts as expected. There's comfort in predictability. But that raises a deeper question. If this wasn't the danger, what is? You might close your eyes now and imagine the sky not as a void, but as a thick forest, some trees you can see. Some shapes flicker in moonlight, but most are hidden in mist, and it's there, in the places light doesn't reach easily, that the forest breathes with quiet, unseen life. Our cosmic forest is the same. The Milky Way hums with motion and matter, and not all of it shines. Not all of it wants to be seen. Astrophysicists still debate what percentage of mass in our galaxy is truly visible. The stars, planets, comets, clouds, they're just a sliver, maybe 5%. The rest, dark matter, dark energy, forces we infer by their effects but cannot touch or trace directly. That means the overwhelming majority of our galaxy is invisible, and yet profoundly influential. So when something like 3i Atlas cruises through our solar system, it's tempting to focus all our attention there. But maybe, just maybe, it's a distraction. A flicker we latch onto while the deeper currents of space glide silently around us. This is not a cause for fear, but for humility. One lesser-known detail, 3i Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System in early 2024. The system, based in Hawaii, uses automated telescopes to spot fast-moving objects. What's remarkable is that we nearly missed it. A few days later, and it would have been out of view entirely. Even with our best tools, we glimpse only a thread of the larger tapestry. And that leads us into a quiet truth. We are still learning how to listen. In space, silence doesn't mean emptiness. It often means distance, scale, or subtlety. Our instruments are improving. Space-based observatories, infrared arrays, radio telescopes listening through the static. But the sky is vast. Most of it whispers, not shouts. The real threats, if they exist, aren't the ones we catch on the edge of our vision. They're the ones that don't announce themselves at all. Quiet masses drifting just outside our detection range. Forces we haven't yet named. Patterns we haven't yet noticed. And perhaps, like the turning of tides or the faint shift of seasons, the cosmos changes slowly, imperceptibly, not with a bang, but with a drift. So we'll keep looking, not in panic, but in patient awe. 3i Atlas. It's a name that feels technical, but behind it lies a strange serenity. The 3i simply means it's the third known interstellar object to pass through our solar system. The Atlas part comes from the telescope array that first caught its faint motion, an acronym for the Asteroid Terrestrial Impact Last Alert System. But tonight, as we drift under a dome of stars, we don't need to remember acronyms. We only need to follow the path of a visitor. It arrived in late 2023, emerging from the general direction of Hercules. Its arc was long, shallow, unbound, not looping but slicing, like a single breath across a sleeping world. Unlike comets that belong to our own star's deep vaults, this object came from beyond the heliopause, beyond the frozen shores of the Oort cloud. And just as quietly as it appeared, it left again. Its velocity was too high for the sun's gravity to hold it. Like a feather tossed past a candle flame, it curved slightly but never paused, never circled, just moved through. And that's the clue. Objects that threaten us, asteroids that might strike Earth, comets that might arc in and return, they tend to be gravitationally bound. They spiral, they revisit. But 3i Atlas was not one of those. Its trajectory was hyperbolic. That means it's not part of our system's rhythm. It has no interest in staying. It merely brushed past. What's more, it never came close to Earth. The closest it reached was tens of millions of kilometers away, farther than Mars at opposition. And during that time, it barely brightened. It didn't flare like a comet. It didn't fracture, twist, or leave behind a trail of icy debris. It behaved, in a word, gently. Telescopes did their best to study it. Spectral fingerprints suggest it was likely composed of carbon-rich material, not unlike certain primitive asteroids. Some called it comet-like, but without the coma or the tail. Others noted its tumbling motion, how it rotated unevenly, as if still shaking off a long, cold voyage. A lesser-known detail, even the James Webb Space Telescope wasn't able to observe it. The object was too dim, too fleeting, too far south in the sky during key windows. This tells us something sobering. Even with our most advanced instruments, we cannot always see what passes through. But in this case, that's okay, because 3i Atlas wasn't the kind of object we need to worry about. It followed the rules of physics as we know them. It moved along paths we can model. There were no unexplained accelerations, no signs of propulsion, no mystery trails, just a fragment from another system, likely ejected long ago, now on a one-way journey into the stars once more. And this gives us an opportunity to reflect not just on what didn't happen, but on why we fear it at all. You see, the human mind evolved to watch the visible world. We're drawn to things that move suddenly, shine brightly, deviate from pattern. A streak across the sky catches our eye far more than a slow, dark drift. That's natural. It's part of how we survived. But astronomy reminds us that the cosmos doesn't owe us that clarity. The real structures, the massive, quiet threats or curiosities, don't often announce themselves. They don't shimmer in neon. They wait in silence. Take this small example. An object like 3I Atlas spends almost all its life in total darkness. For billions of years it may have coasted through the space between stars, passing no planets, no suns, no warmth, just void. Absolute quiet. Then, for a few short months, it entered a star's light and became visible to us, and then gone again. It's humbling. Some astronomers believe that systems like ours routinely eject these fragments. When gas giants form or migrate, they disturb the paths of smaller bodies, flinging some outward. These remnants wander the galaxy, homeless and alone. We're likely surrounded by them, trillions of such fragments coasting between stars. 3I Atlas just happened to cross our path at the right time, and because it came and went without incident, it reminds us of a cosmic truth. Not everything foreign is dangerous, not everything unknown must be feared. There was a brief moment, just after its discovery, when speculative headlines hinted it might be a threat. Some suggested it could change course, others hinted at an artificial origin. A few worried it might enter Earth's orbit. But that didn't happen. It didn't veer. It didn't pulse or signal, it simply moved as expected. Like a pebble skipping across a lake, it touched our solar system only briefly. Astrophysicists still debate how often these objects pass by unseen. Some say once a year. Others suggest dozens might move through unnoticed each decade. Our instruments can only detect what reflects enough light, or what blocks it. The rest remains a mystery, and perhaps that's the real story. 3I Atlas was never a threat, but it was a reminder that the universe is vaster than we know, that visitors can come and go without knocking, that sometimes, in a sea of fear and speculation, the real danger isn't out there, it's the narrowing of wonder. So tonight, as we lie still and listen to the slow breath of time, we let that visitor go. No alarms, no danger, just a brief flicker on our shared path. The night sky has always drawn our gaze, not just because of what we can see, but because of what we can't. Darkness isn't emptiness, it's a veil, one that conceals quiet movements, slow stories, and countless things we haven't yet learned how to notice. 3I Atlas was visible for a time. It shimmered faintly, left a temporary imprint on our records, and then moved along. But not everything in space makes itself known so generously. In fact, most things don't. And perhaps that's the real concern. Not the visitor we can track, but the wanderers we'll never know were there. We're used to treating the sky like a theatre. Bright stars or glowing planets, streaking meteors, they catch our attention, play their parts, and vanish behind the curtains. But the real stage is far deeper. A dark sea where the vast majority of matter, movement, and mystery happens in silence. You might imagine, just beyond the reach of our detectors, a slow parade of silent shadows, drifting, not aiming but present. Some may be small, like frozen crumbs from long-dead solar systems. Others may be vast, cold, heavier than we'd like to admit, but they don't glow, they don't sing, they don't scatter light, and so, for now, they escape notice. We only know they're there because of absence. Stars behave strangely at the edges of galaxies. Light bends around invisible things, and motion across the heavens sometimes doesn't match the visible script. These are all hints, whispers, the soft evidence of a cosmic stagehand pulling strings from behind the curtain. Astrophysicists still debate how many unseen objects might be drifting through interstellar space. Some estimates suggest billions of rogue planets. Others hint at entire black holes roaming freely, their gravity the only sign of their passing. If 3i Atlas was a pebble tossed past our campfire, these others are deep-sea currents that never touch the shore. We fear comets because they streak in bright, unstable arcs. We worry about asteroids because they sometimes intersect Earth's path. But the true unknowns, they are quiet, they are cold, and they are invisible, and that's what makes them worth thinking about. One lesser-known category of potential wanderers are interstellar dark comets. These aren't like the icy bodies we sometimes see lighting up the sky. They are theorized to be made of extremely low albedo material, dark as soot, absorbing nearly all light. Even if one passed between us and a star, it might not block enough light for us to notice. Their existence is hypothetical, but plausible. If our solar system ejects objects, so must others, and if some of those objects are coated in carbon-rich material or have surface textures that reflect little to nothing, then we would never see them coming, not because they're hostile, but because they are quiet in every way light knows how to listen. Imagine lying in a forest at night. You hear a twig snap, a breeze stirs the leaves, you see the moonlit edges of trees, but beyond that there are sounds you don't hear, movements that never rise above the hush. That's what the cosmos offers us, a beautiful, endless forest where most of the movement is mute. And here's the poetic twist. The things we most often fear are least likely to harm us. Bright meteors burn up harmlessly, comets put on a show, then fade. But the quiet objects, the ones without name, shape, or warmth, they slip past unmeasured, or worse, they linger just beyond the edge of perception. None of this should make us afraid. If anything, it should deepen our awe. We are not surrounded by threat, but by mystery. The universe doesn't roar, it hums. Even the objects we can't detect may never come near us. Space, after all, is mostly space. Vast distances stretch between stars, and the chances of a rogue object intersecting our narrow orbital path remain small. But just knowing they exist, that there is so much we don't see, reminds us how incomplete our map of the cosmos really is. And this is why we look outward, not just for defense, but for perspective. We watch the visible sky to glimpse the invisible patterns behind it. Some astronomers are working on new detection methods, not just optical telescopes, but instruments that watch for minute gravitational shifts, or radio echoes, or even infrared heat signatures from cold passing bodies. We're listening harder than ever. But the truth remains, we miss more than we catch. Perhaps that's the real cosmic threat, not a specific object, but the hubris of assuming we've seen it all, that we know what matters simply because it appears in our line of sight. So when we heard about 3 Atlas and saw the news cycle spin up with warnings and dramatic headlines, we might have asked a quieter question. What else is drifting through the dark? Not because it's dangerous, but because it's there, and because that, in the end, is what makes the sky worth watching. Far beyond the orbits of our known planets, beyond the familiar sweep of Pluto's path, and even the scattered whispers of the Kuiper Belt, lies a region so distant, so cold, and so silent that we've never seen it directly. Yet we believe it exists. It's called the Oort cloud. And tonight, as we let the soft rhythm of ancient light settle over us, we turn our attention there, to a place that might not truly be a place, but a halo of possibility, draped around the solar system like a forgotten ring of frozen breath. The Oort cloud is not a disk like Saturn's rings or the flat plane of the inner solar system. It's thought to be a vast, spherical shell of icy bodies that surrounds our solar system in every direction. A soft bubble made of comets and ancient remnants. Each piece may be no larger than a mountain, but together they could number in the trillions. We've never seen one with certainty. They're too far, too dark, too cold. No sunlight reaches them strong enough to bounce back and tell us where to look, but sometimes one falls inward. And when it does, it burns through the sky as a long-period comet, a trail of ice, fire and history that we call beautiful. even if it comes from the quiet edge of everything. You might picture it now, not as a map, but as a hush. A three-dimensional silence, wrapping us in a cosmic shell that reaches halfway to the next star. It's in this place, this deep reservoir, that the real cosmic mysteries may sleep. For every object like 3i Atlas that arrives from beyond the solar system, there may be thousands of fragments already orbiting loosely around us, waiting. Not with intent, not with malice, but simply drifting, caught in the cold mathematics of ancient orbits. Astrophysicists still debate how large the Oort cloud really is. Some say it could stretch up to 100,000 astronomical units from the Sun. That's over a light year. Others argue it may not even be a continuous structure at all, but a statistical boundary, a region where the Sun's gravity finally loosens its grip. A lesser-known hypothesis suggests that interstellar objects like 3i Atlas could actually be old residents of someone else's Oort cloud. That during the early chaos of stellar formation, gravitational nudges flung fragments outward, shards of icy potential that now drift across the galaxy, untethered. And just as stars wander, so do their ghosts. If that's true, then the Oort cloud isn't just a local curiosity, it's a shared feature of planetary systems everywhere, a quiet memory of formation. A kind of universal exile zone for the smallest, coldest pieces of cosmic debris. You might imagine these fragments as cosmic seeds, dormant, waiting, silent. Some may remain frozen forever. Others might eventually be drawn inward again, toward heat and light. But most will never be seen, not by us, not by any eye. And yet, they exist. The thought is both eerie and soothing, that as we drift through the galaxy, we are wrapped in a cloud of ancient icy companions. Some may have been with us since the beginning, others may have arrived more recently, captured during the Sun's long journey through interstellar space. The boundary between what belongs to us and what doesn't becomes less important, less sharp, more porous. And this opens a deeper question. What else might be sleeping out there? Are there larger bodies? Planetoids with crusts and cores, born in isolation and never warmed by a star? Are there rogue binaries, pairs of icy objects caught in mutual orbit, whispering through the dark together? Could there even be something once warm, now frozen solid, carrying the chemical echoes of an ancient ocean beneath a shell of ice? We simply don't know, and because we don't know, we must remain gentle in our conclusions. This is where astronomy begins to blend with philosophy, not because we seek meaning in the void, but because we recognize the limits of our gaze. The Oort cloud reminds us that seeing is not the same as knowing. That distance can mask not just detail, but whole categories of truth. You might picture the Oort cloud again now, not as a static place, but as a breathing envelope, faintly pulsing with gravitational tension. Occasionally, a distant star might pass close enough to disturb its stillness. A ripple, a rearrangement, a distant fragment nudged inward, beginning a journey that could take millions of years before anyone sees its glow. These objects may hold clues about the early solar system, unchanged, unheated, unshaped by time. To hold one in our hands would be to touch history itself. But for now, we watch from afar, and we wonder. Not because it's a threat, but because it's a horizon. And as we've said before, the real threats in astronomy aren't usually the ones that announce themselves. They're the ones we overlook, the ones that hide in expectation, just outside the spotlight. 3i Atlas is gone now, but the Oort cloud remains, silent, undetectable, profoundly patient, and perhaps one day something else will drift inward, something quiet, something old. And once again we'll look up and ask, where did that come from? Let's drift now towards something even more elusive, something we cannot touch, cannot see, cannot hear, yet it shapes the very way galaxies hold together, dark matter. It's a strange phrase, isn't it? At once scientific and poetic, it sounds ominous, but it isn't meant to be. It simply describes something unknown, matter we can't observe directly, but which must exist, because the universe wouldn't make sense without it. Dark matter doesn't shine. It doesn't reflect light. It doesn't absorb radiation in ways we can easily detect. But its gravity is very real. It tugs at stars. It bends light. It holds clusters of galaxies together like a vast cosmic glue. You might imagine galaxies spinning in the dark, huge whirlpools of stars and gas. But when astronomers first studied their rotations, they noticed something odd. The stars at the outer edges were moving too fast, far faster than Newton's laws would predict, based on visible mass alone. It was as if something invisible was holding them in place. That something is what we now call dark matter. Astrophysicists estimate that roughly 85% of all matter in the universe is dark. That means everything we can see, all the planets, stars, dust, clouds, nebulae, galaxies, is just a tiny sliver. The rest drifts in silence. And here's a lesser-known curiosity. Some researchers believe there might be entire dark matter halos surrounding galaxies. These halos may stretch far beyond what we can see. Massive spherical cocoons of invisible gravity gently guiding how stars orbit over billions of years. The Milky Way has one too. A ghostly shell we can't detect directly, but which shapes the way our galaxy breathes. We live inside it, move with it, and yet we don't feel its touch. It's possible that some of the gravitational anomalies we blame on rogue planets or unseen black holes are actually caused by local clumps of dark matter. Regions where this invisible substance is pulled ever so slightly, nudging light and motion in subtle, persistent ways. Astrophysicists still debate what dark matter is. Some suggest it's made of particles we haven't discovered yet, things like WIMPs or weakly interacting massive particles. Others propose entirely different theories, like modifications to gravity itself, or exotic forms of matter left over from the earliest moments of the universe. But the truth is, no one knows for certain. You might picture it as a quiet scaffold, an invisible structure that galaxies form around, like dew collecting on an unseen web. Without dark matter, stars might never have clustered at all. Without it, the universe as we know it might never have settled into patterns. It doesn't crash into things. It doesn't block starlight or reflect it. It simply is. And this makes it the perfect candidate for a hidden cosmic threat. Not because it wishes us harm, of course not, but because it exists without being noticed. It reminds us how much of reality can lie just beneath the surface of what we think we know. If dark matter were to drift in dense concentrations through our solar system, just small undetectable clouds, it could theoretically perturb the orbits of planets or alter comet paths subtly over time. We might never trace the cause, we might never know it was there, but perhaps it already has. Perhaps some of the long-period comets that sweep in from the far reaches of the Oort cloud were nudged long ago by silent masses of dark matter passing nearby. Perhaps these mysterious tides shape more of our solar weather than we've realized. You might close your eyes and imagine it now, the space between stars not empty, but full of softness, of drifting influence, of quiet mass that doesn't shine but shapes. That's what makes dark matter such a beautiful mystery. It's everywhere and nowhere, essential and invisible. We don't fear it, but we don't understand it either. And maybe that's the real quiet tension in astronomy. Not the danger of known things, but the stillness of the things that haven't revealed themselves yet. As we lie under a velvet sky tonight, we're not just looking outward, we're also looking through light, through shadow, into the structure of space itself. And we might remember, softly, that what holds us together isn't always what we can see. Somewhere in the darkness between galaxies a wave ripples. It does not shine, it does not glow, it does not need light at all. It is gravity, shifting, bending, flexing space itself. And for a moment, the universe quivers. These are gravitational waves. Unlike light, which dances across the sky in flickers and colours, gravitational waves move through the very fabric of space-time. They stretch and squeeze everything they touch. Not enough for us to notice in daily life, but enough that, with patient instruments and deep silence, we can listen. You might think of them as the softest whispers in the cosmos. Born from violent events, colliding black holes, merging neutron stars, the collapse of ancient suns, they travel outward in all directions, unchanged, untouched, growing fainter with every passing year. They reach us eventually, sometimes billions of years after the event, long after the stars involved have faded, long after any light from the collision has vanished into deep time, and yet they still arrive. One lesser-known detail: when two black holes spiral into each other and merge, they release more energy and gravitational waves than all the stars in the observable universe emit in light, combined during that same instant. And yet, we don't see it. We feel it. Just barely. It took humanity until 2015 to detect a gravitational wave directly. The observatory was called LIGO, the Laser Interferometer Gravitational Wave Observatory. Using 2 arms of laser light kilometers long, it measured shifts in distance smaller than a proton's width. When the first signal came in, it lasted less than half a second. A ripple, a hum, a warble in space-time itself, and suddenly we had a new way to hear the universe. The discovery didn't just confirm Einstein's predictions, it opened a new kind of astronomy, one that doesn't rely on light or colour or radiation. One that listens for the deep movements of massive things. You might imagine now a black hole, dark and patient, moving silently for millions of years. Then another approaches. They orbit. Closer, closer. The dance accelerates, becomes a spiral, a blur, and then merger. No light, no explosion, just a sudden change in the shape of space. And from that moment, a wave begins. Soft, perfect, eternal. And billions of years later, we, on our tiny blue planet, catch that whisper. Astrophysicists still debate what we might learn from these waves. Could they reveal hidden populations of black holes? Could they tell us about the first stars, the earliest galaxies, or events we've never seen at all? Some even hope to detect primordial waves, ripples left over from the Big Bang itself. That's the haunting beauty of gravitational waves. They are not constrained by matter. They don't bounce off dust or disappear in fog. They travel freely, revealing what light cannot. Perhaps one day we will map the universe not just with telescopes, but with gravitational ears, charting the great collisions of time by the waves they leave behind. A lesser discussed idea. Some gravitational wave events may come from things we've never considered, like exotic cosmic strings, or even hypothetical objects beyond black holes. Every signal we catch might carry a new surprise, or a new question. And while we're still early in this science, it feels like we've just placed a seashell against the ear of the cosmos, and are hearing, for the first time, the slow breath of deep time. Gravitational waves don't pose a threat to us. Their force, by the time it reaches Earth, is unimaginably gentle, a stretching and squeezing of space that's far smaller than an atom. You might sleep through 1,000 of them without ever knowing, but they remind us again of the unseen, the unlit, the movements that shape everything, even as they leave no visible trace. You might imagine your body now, not floating in space, but being stretched, ever so slightly, by a passing wave. You don't feel it, but you are part of the signal, part of the echo. And that is what makes this universe so quietly magical. Even the things we cannot see are touching us. Even the past still arrives, and even in the hush of midnight the universe is moving. Let's imagine now something adrift, Not a comet, not an asteroid. Something deeper, something heavier, something that doesn't shimmer or trail light. A black hole, alone. We're used to thinking of black holes as distant monsters, anchoring the hearts of galaxies or devouring stars with luminous flares. But not all black holes are so dramatic. Some don't orbit anything, some don't shine at all, some just wander. These are called rogue black holes, dark remnants of collapsed stars that have slipped free from the gravitational hand of their home system, no longer tethered, no longer part of a stable dance. They drift through the galaxy, unseen and silent like ancient sharks in a cosmic sea. And we think there could be millions of them. You might be surprised to learn that stellar mass black holes, those formed when massive stars die, are predicted to be quite common. Estimates suggest that the Milky Way alone could harbour over 100 million of them, and most have never been detected. Why? Because they're invisible. They don't emit light. They don't glow. They only reveal themselves when interacting with something else, by bending the path of nearby stars or by pulling matter close enough to heat and radiate. But if they wander far from any bright companions, they leave no trace. They become truly rogue. One lesser-known technique for detecting them involves gravitational micro-lensing. It's a phenomenon where a massive unseen object passes between us and a background star, temporarily magnifying the starlight. Not because the object emits light, but because it bends space-time itself, creating a lens through which light bends and flares. In 2022, astronomers announced what may have been the first direct evidence of an isolated black hole using this method. It had no companion star, no accretion disk, just mass and motion and silence. Astrophysicists still debate how many of these roamers exist. Some may have been flung out during supernova explosions. Others may have been cast away by gravitational interactions in dense star clusters. A few may have formed in the early universe and never joined any galaxy at all. And the unsettling part? One could be moving toward us right now. But don't worry, space is vast. Even in the busiest regions of the Milky Way, stars are separated by light years. A rogue black hole would need to be remarkably close, within a few hundred astronomical units, to even begin affecting anything in our solar system. And so far, we've seen no sign of that. Still, the idea lingers, that out there in the cold regions between stars, something ancient and heavy moves slowly. No light, no voice, just the pull of gravity. You might imagine it now, a cold, invisible sphere the size of a city but with a mass of several suns, moving steadily through the dark, pulling nothing, leaving no wake. It does not hunt. It does not aim. It simply exists. And if it were to pass near us, very near, we might never see it coming. It would tug gently at the outer planets, shift the path of a few comets, perhaps stir the Oort cloud ever so slightly. We might notice those effects first, long before we knew what was causing them, and in that time of uncertainty, before pinpointing the culprit, we'd ask all the familiar questions. Was it a new planet? A rare comet? Something artificial? Until finally the numbers point to a quiet mass, unseen, undetectable except by its pull, a rogue black hole. But again, this is not a warning. It is a reminder of the things that move without needing to be known. The universe is not out to frighten us. It's simply large and old and filled with objects that do not shine. Most of them will never come near. But their existence stretches the limits of our imagination. It challenges what we consider visible. It asks us to pay attention, not just to the light, but to the ways light moves, to the subtle curving of starlight, to the long silence between bursts, to the gravity we feel but cannot see. And maybe, as you breathe softly now, you can picture the galaxy not just as a sea of stars, but as a slow drift of invisible giants, moving among us, unseen but real. They are not here to threaten. They are here to teach us humility. Picture now a star in its final breath, not exploding in brilliance like a supernova, but collapsing inward, folding gravity into itself until something new and strange is born. Not a black hole, something in between, a magnetar. These are among the most magnetic objects in the known universe. Born from the death of massive stars, magnetars are a type of neutron star, ultra-dense remnants just 20 kilometers across, yet heavier than our Sun. But what makes them different is their magnetic field. It's not just strong, it's unimaginably strong. A magnetar's magnetic field can be 1,000 trillion times stronger than Earth's. If one were as close to us as the Moon, its magnetic power might erase every credit card on Earth. And yet most of them are so far away that we detect them only when they hiccup, releasing a burst of energy that echoes across the galaxy. That's their voice, a sudden soft crack in space. Magnetars are rare. We know of only a few dozen in our galaxy, but astronomers suspect many more are hidden. Most are silent, dormant, spinning slowly deep in the starry ocean, waiting. You might imagine one now, not as a threat, but as a lighthouse, a spinning beacon that occasionally flares, sending out a burst of X-rays or gamma rays as its crust rearranges or cracks under pressure. It's not violence, it's stress, the strain of extreme physics. A lesser-known detail, some fast radio bursts, those mysterious millisecond blips we sometimes detect from distant galaxies, may be caused by magnetars, a sudden shift, a magnetic quake, a flare, and then silence again. Astrophysicists still debate whether all fast radio bursts come from magnetars. Some do, others don't fit, some repeat, others do not. The debate continues, humming softly through observatories and data pipelines around the world. But one thing is clear, magnetars are not just curiosities. They're cosmic reminders that stars do not die quietly. Sometimes they transform. In their dense cores, atoms are crushed into a sea of neutrons. Temperatures soar. Magnetic lines twist and tangle. And in those moments, strange things can happen. One magnetar, known as SGR 1806-20, released a flare in 2004, so intense that it briefly altered Earth's ionosphere, from 50,000 light-years away. For a tenth of a second, it became the brightest object in the gamma-ray sky, and then, like a breath held too long, it disappeared. No explosion, no debris, just an echo. And this is where the story becomes quietly eerie. What if one were closer? What if a rogue magnetar passed through the outskirts of our system? Not enough to be dangerous, perhaps, but close enough to disturb magnetic fields. Could it affect the heliosphere, disrupt satellites? The answer is maybe. Astrophysicists still debate how far a magnetar's influence could reach. It depends on the intensity of its flares, the structure of its field, the angle of approach. There are many variables, and we haven't observed one up close. But again, this is not about fear, it's about perspective. We live in a galaxy filled with exotic remnants. Black holes, neutron stars, white dwarfs, pulsars and magnetars. Each is a different flavour of stellar afterlife, and each teaches us something new about what stars become when the light fades. Magnetars in particular remind us that invisibility does not mean stillness, that quietness is not always peace, and that deep within the cosmos tension builds. Not always to destroy, but sometimes just to release. You might imagine a magnetar now, spinning alone, its field twisting like braided thread. Every so often it flares, just a whisper across the stars. A soft crack in the structure of reality, and then stillness again. No announcement, no farewell, just the long, quiet spinning of a star that died, but didn't stop. The universe is full of such stories. Not dramatic, not loud, just ongoing, like breath, like tide, like sleep. There's a peculiar beauty in light that bends. A distant galaxy, serene and aglow, sends its photons outward in all directions, waves of ancient light travelling for billions of years. But then something intervenes. Not a wall, not a mirror, but gravity itself. This is gravitational lensing, and it's one of the most delicate poetic phenomena in modern astronomy. You might picture it like this. Space is not flat. It curves gently around mass. The more mass there is, the deeper the curve. When light passes near something massive, like a galaxy cluster or a hidden black hole, it doesn't travel in a straight line. Instead, it arcs. It bends around the curve, following the fabric of space itself. We call the result a lens, not because glass is involved, but because the effect is the same. The light is magnified, warped, duplicated, and through that distortion we glimpse not only the object in the foreground, but something farther beyond it that we otherwise couldn't see. Gravitational lensing reveals the hidden. In some cases it creates full rings, perfect circles of light like cosmic halos. We call them Einstein rings, a quiet tribute to the theory that made them possible. More often we see arcs, stretched galaxies, strange smears of colour that tell us something massive is lurking here, and often the thing doing the lensing is invisible. That's what makes it so useful. Through gravitational lensing, we've mapped dark matter in galaxy clusters. We've found entire galaxies behind other galaxies. We've even glimpsed objects so distant their light began its journey when the universe was still young. A lesser-known application. Sometimes we use lensing to study individual stars. Stars in the farthest reaches of the cosmos, too faint to see otherwise. Their light is magnified just long enough for us to notice, and then, like a blink, it's gone again. Astrophysicists still debate how best to model lensing events caused by small rogue objects. For example, could a drifting black hole bend the light from a background star just enough for us to catch it? Some believe so, others argue the signal would be too brief. But every year our models improve, our sensitivity deepens. And this leads to a quietly unsettling idea. There may be massive dark objects scattered throughout space that we will never see, unless by chance they pass between us and something bright. They could be dark matter clumps, rogue black holes, or even theoretical structures like primordial black holes, tiny yet ancient relics from the first moments of time. We wouldn't know they exist except through the light they bend. Imagine walking through a forest where the trees are invisible, but you can still see their shadows on fog. That's gravitational lensing, and it reminds us that even darkness can leave fingerprints. You might think, in moments like this, of the stars you have seen with your own eyes, maybe on a mountain or a quiet road, or through the window of an airplane. Each of those stars shines in a straight line to your eye. But what if once or twice one of those beams of a light had bent just slightly, curved around some distant mass, a cosmic hitch in the path, before finding its way to your vision? You wouldn't notice. But you would be receiving light touched by gravity, and that in itself is astonishing. We often say the universe is dark, but perhaps that's not quite right. It's not dark, it's layered, and lensing peels back those layers, briefly, gently. It's how we know there is more than we see. A flash of brightness where there shouldn't be one. A faint arc where no object exists. A repeated pattern that makes no sense until gravity itself becomes the lens. In the coming decades, telescopes like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope will scan vast portions of the sky, hoping to catch more of these quiet distortions. More hints, more shadows of invisible things, not to fear them, but to understand them. Because even in distortion there is clarity. Even in bending, the universe tells us something true, and in every warped glimmer of light, we are reminded that the cosmos is not just what we see, but what responds. There is a glow that surrounds us, a hush from the ancient universe, always present, though we never feel it directly. It comes not from stars, not from galaxies, but from the moment the cosmos first became transparent. It is called the cosmic microwave background. The CMB, as it's known to astronomers, is the oldest light we can observe. Not from a star or a planet, but from the fireball of the Big Bang itself, softened and stretched by time until it whispers now in microwaves, gentle, low-energy photons drifting through space. Imagine it, the universe, just 380,000 years old, a baby, compared to its current age of over 13.8 billion years. Before that moment, everything was so hot and dense that light couldn't travel freely. It was trapped, bouncing between particles like echoes in a fog. But then something changed. The universe expanded and cooled just enough for atoms to form. Electrons joined with protons, and suddenly light was set free. That light has been travelling ever since. We don't see it with our eyes. It's far too faint, too redshifted. But we can measure it with microwave detectors, delicate instruments that pick up the faint heat left over from that moment of cosmic liberation. In 1965, two scientists, Arno Penzias and Robert Wilson, accidentally discovered it while trying to eliminate background noise from a radio antenna. What they found instead was the soft, persistent hum of the early universe, filling the sky in every direction. A lesser-known detail: the CMB is not perfectly smooth. It contains tiny fluctuations, small temperature differences that reveal the seeds of cosmic structure, galaxies, clusters, voids. These ripples are like fossilized sound waves, echoing from a time before stars, before planets, before anything we recognize. Astrophysicists still debate the finer details of those fluctuations. What do they say about inflation? About the shape of the universe? About what came before? Each new satellite, COBE, Arsumat, Planck, has revealed the CMB with greater clarity, sharper maps, finer texture. The latest images show a mottled glow, like an ancient tapestry, wrinkles in the light itself. And through those wrinkles we learn how the universe grew. You might think of the CMB as a soft background hum, not silence exactly, but the faintest possible echo. It's still around you now. Every second your body is bathed in these photons. They pass through you, through your room, through everything. They do no harm, they carry no heat you can feel, but they're real. They are the memory of a beginning, and they tell us that the universe had a moment where it exhaled. That light, ancient, tired and faded, reminds us that the cosmos is not just filled with brightness, but with age. Perhaps the most profound thing about the CMB is that it looks almost the same in every direction. No matter where we point our instruments, we see the same gentle glow. This tells us something simple and beautiful. The universe has no center, no edge, no preferred direction. It expands evenly, softly, like a balloon filling with breath, and in that expansion we are carried. You might close your eyes and imagine it now, not a blast, not a flash, but a gentle swell. The universe cooling, light breaking free, and space unfolding softly outward. In a way, the CMB is still expanding, not the light itself, but the space it travels through. Each photon is stretched by the slow breathing of the cosmos, its energy fading, its wavelength growing, and yet it persists, a glow behind every star, a hush beneath every signal, a light that outlived its origin. It does not flicker, it does not pulse, it simply is. It reminds us that the universe had a beginning, and that we are still inside that beginning's long, slow echo. We often search the skies for danger, but this light is the opposite. It's not a threat, it's a lullaby. Let's drift deeper now, into something hard to grasp, something without form or brightness, something we move through every moment but can't point to directly. Time. We treat it like a river, always flowing forward. We set our clocks, we mark our calendars, we speak of history as behind us and the future as ahead. But in the wider frame of the cosmos, time is not so simple. In fact, it might not be a river at all. What we call time could be a consequence of entropy, the way systems move from order to disorder. A cup of hot tea cools, a star burns through its fuel, a galaxy spreads slowly into the silence. But if all those particles were arranged in reverse, moving from chaos into structure, would time flow backward? Perhaps. Astrophysicists still debate what gives time its direction. The fundamental laws of physics, the equations that govern particles and forces, don't prefer one direction over another. A collision looks the same forward and backward. It's only when entropy is involved that a clear before and after seems to emerge. And this opens a fascinating possibility that time as we experience it is not fundamental. It might be a shadow of deeper laws, a local phenomenon tied to complexity and heat and memory. A lesser-known idea from theoretical physics is that time might have emerged as the universe expanded. In its earliest moments, before inflation stretched everything outward, before particles and forces had distinct identities, there may not have been time as we know it, only potential. Imagine that, the cosmos not as an explosion into time, but as the birth of time itself. A soft blooming, where what we now call moments gradually became distinguishable from one another, and here we are, billions of years later, still counting those moments. But what if time behaves differently elsewhere? Black holes stretch it. The closer you get to the event horizon, the more time slows down. From a distance, a falling object seems to freeze in place, stuck forever on the brink. Inside, time and space swap roles entirely. The future becomes a direction you cannot avoid. Meanwhile, in deep space, far from stars, planets, and gravity wells, time may move more cleanly, more evenly. Yet it is not absolute. You might imagine now a region of space utterly quiet. No matter. No light. Just a vacuum as still as anything can be. Does time pass there? What changes? What measures it? If nothing moves, does anything age? We often take time for granted. It ticks along on our watches, sets our schedules, and carries us gently through sleep and waking. But in the universe's deeper structure, time is flexible, soft, malleable. In cosmology, time is tied to expansion. As the universe grows, space stretches, and so do wavelengths of light. That's what redshift is. The deepening of colour, the stretching of history. And so, in a sense, the farther we look, the younger things appear. But also, the older the light becomes. It's a paradox only because we are used to thinking of time as universal. But the cosmos teaches us otherwise. One day, far in the future, our own galaxy may be alone in the sky. As the universe continues its expansion, other galaxies will drift out of view, pulled beyond our observational horizon. To future astronomers, it might appear as though the Milky Way is the entire cosmos. They will not see the ancient clusters we now map. They will not receive the cosmic microwave background. The past will have drifted too far. Unless, of course, we remember it for them. Unless we pass on the maps, the stories, the flickers of light caught from billions of years ago. Because time, while fragile, can also be preserved. In fossil light, in gravity waves, in the slow chemistry of distant rocks, and in our memories. So tonight, as we breathe under a velvet sky, we might let go of the idea of time as a strict march. Let it soften, let it swirl, stretch, bend. Let it become part of the hush, not a ticking clock, but a deep, unfolding rhythm. Among the stars and across the swirling arms of galaxies, dust drifts, tiny grains of silicates and carbon, metal flecks and icy particles, silent, scattered, ancient. It may not sound like much, but this dust builds worlds, and in some places it organises. These places are called protoplanetary disks. You might imagine them as soft halos of material orbiting newborn stars, cosmic cradles where planets are being formed. slowly, patiently. At first glance, they look like glowing discs of light, but inside they are layered with gas and dust spiralling inward, clumping, colliding, sticking together grain by grain. We've captured images of them now, thanks to instruments like the Atacama Large Millimeter Submillimeter Array, or ALMA, perched high in the Chilean desert. These pictures show dark rings and bright gaps, not flaws but signs, gaps carved by planets in formation. Each ring may be the path of a hidden world. It's humbling to see planets in the act of becoming, to realise that what once happened here, in our own solar system, is still happening elsewhere, right now. A lesser-known fact: these disks don't last forever. They dissipate after a few million years. The window for planet formation is surprisingly short. The gas fades. The dust disperses, and whatever worlds were able to coalesce remain. The rest are lost. That makes them fleeting. And yet within that fleeting time, gravity sculpts. Pressure builds. Heat rises. Tiny pebbles become rocks. Rocks become planetoids. And sometimes, if conditions are right, something extraordinary happens. A planet capable of sustaining life begins to take shape. Astrophysicists still debate exactly how planets form from such chaotic beginnings. Is it a steady accumulation, like building a snowball, or do some chunks collapse suddenly under their own weight, forming massive gas giants almost overnight? Both processes may occur, depending on the conditions, the density, the motion of the dust. We've now detected thousands of exoplanets orbiting other stars. Some are giants, orbiting close in. Others are small, rocky, and distant. But for many, we know little about how they came to be. That story begins in the dust. You might picture a young star now, burning hot, but not yet stable. Around it swirls a thick, warm disk, and inside that disk, trillions of particles collide, fall inward, or drift outward depending on pressure, temperature, and time. It's a quiet process. No fireworks, no sudden gestures, just endless motion. A hush of gravitational gathering. Sometimes we wonder whether our solar system formed under special circumstances. But the more protoplanetary disks we observe, the more we realise that planet formation is common. The ingredients are everywhere, and yet so much must go right. The star must be stable. The disk must last long enough. The planets must find quiet orbits. Collisions must be balanced, enough to build, not to destroy. And even then, chance plays a role. One well-placed collision can destroy a forming planet. One nearby supernova can strip the gas away. One gravitational tug from a passing star might unravel everything. So each world that survives, that endures long enough to cool, to stabilize, to host chemistry, feels like a quiet miracle. Perhaps, in some dusty ring around a star 100 light-years away, there is a planet forming right now, not yet solid, not yet spinning cleanly, but slowly gathering itself together. Its surface may be molten, its sky thick with vapour, but deep inside, minerals are forming, crystals are aligning, magnetism is emerging, the seeds of geology, of atmosphere, of weather, of possibility. We may never see that world. It may never develop life, or water, or land, or it may one day glow blue against a quiet sun. But whether or not we meet it, it reminds us that the process of creation is ongoing, not in a flash, not in chaos, but in the slow drift of dust. The universe continues to build, even as it expands, and perhaps that's the gentlest truth of all, that creation is not finished. Far from the warmth of our sun, past the orbit of Neptune, past even the icy drift of Pluto and the scattered debris of the Kuiper Belt, lie worlds so cold, so quiet, they were once thought lifeless by definition. And yet, they whisper. Tonight, we listen to those whispers from beneath layers of ice, across frozen oceans and through the thin plumes that rise into the void. These are the ocean worlds: Europa, Enceladus, Ganymede, Titan. moons orbiting distant gas giants, covered in ice, sealed in frost, but beneath their frozen exteriors lie entire oceans, saltwater seas, deep and dark, warmed not by sunlight, but by tidal forces, the gentle squeezing and stretching caused by gravitational interactions with their parent planets. The ice on Europa is cracked, like the surface of a frozen lake at dawn. Its scars suggest movement, flow, a dynamic shell over something liquid. In 2012, the Hubble Space Telescope detected plumes, jets of water vapour erupting from its surface, like soft geysers reaching into space. Enceladus, smaller and whiter, shines like a pearl. In 2005, the Cassini spacecraft flew through its southern polar plume and found water vapour, ice grains, and organic molecules. A quiet breath from an underground ocean. A lesser-known fact, these moons have more liquid water than Earth. Enceladus's ocean may be tens of kilometres deep, Europa's even more. Trapped beneath kilometres of crust, these seas might stretch across the entire moon, global oceans sealed in silence. And in those oceans, the question emerges, could life exist? Astrobiologists think so. Not surface life, not trees or fish or flowers, but microbes perhaps, extremophiles, organisms that thrive in darkness and pressure and chemical energy. Like those found around Earth's hydrothermal vents deep beneath the Pacific, where sunlight never reaches and yet life flourishes in abundance. Astrophysicists still debate the ingredients for life. Do we need sunlight, or only heat, water, and the right chemistry? Could ammonia serve instead of water? Could life arise in methane lakes like those on Titan? The answers are murky, but the questions are powerful. And here's the quiet miracle. We don't have to leave our solar system to wonder. These ocean worlds are here, in reach, waiting. We've sent probes, we've captured images. But no mission has yet drilled through the ice, no camera has yet drifted through those hidden oceans. The silence remains. But it is a living silence, a silence with motion beneath it. You might imagine drifting down through Europa's crust, layer by layer into darkness, into cold, until suddenly the ice gives way to water, not still, but moving, perhaps under pressure, perhaps stirred by vents, perhaps home to minerals, energy gradients, currents, and maybe, just maybe, to something alive, not threatening, not intelligent, but real, a cell, dividing, a membrane, pulsing, a whisper of metabolism in the farthest shadows of the sun's influence. One day, we may send a submarine beneath the ice. It will carry lights, sensors, and a quiet eye. It will search not for danger, but for structure, for meaning. Until then, we wait. And the moons drift on, around their giants, orbiting Saturn and Jupiter, glowing faintly under distant starlight. They are not dead rocks. They are sealed worlds. Worlds that challenge what we thought we knew about habitability. Because we once believed life could only exist in warmth, in brightness. But now we learn that warmth can come from within. That oceans don't need surface. That the edge of a star's reach is not the edge of possibility. And this reframes our search, not just for life, but for understanding. We no longer ask only where life is. We ask where life might be hiding, in hushed oceans, in buried seas. In silence. Now let's drift even farther, beyond the ice, beyond the reach of suns, into the darkness between stars. A place so quiet, so vast, that light itself becomes a rare visitor. This is where the orphaned worlds wander. Rogue planets. They do not orbit stars. They have no sunrise, no orbit to mark time, no seasons or moons to light their skies. They are alone, cast adrift, moving silently through the interstellar medium, invisible to nearly all our instruments, and yet we think they may be common. Perhaps even more numerous than the stars themselves. It sounds improbable. After all, how does a planet become a wanderer? Don't they form around stars, held close by gravity, locked into orbits like dancers around a fire? Yes, Most do. But sometimes the dance becomes chaotic. In the early days of a planetary system, there is turbulence. Planets jostle for position. Some grow large, others remain small. Interactions can become violent. Gravitational tugs build up until one object, usually the lighter, gets flung outward, losing its tether. And just like that, a world is set loose. A lesser-known detail: some simulations suggest that every solar system ejects several planets during its formation. It's not unusual, it's natural, a kind of cosmic shedding. And over billions of years, these orphaned planets accumulate, silent migrants without suns. Astrophysicists still debate how many rogue planets exist in the Milky Way. Some estimates suggest hundreds of billions. Others go higher. A few years ago, scientists using gravitational microlensing claimed to detect a population of rogue planets as small as Mars. If true, the galaxy may be teeming with them. But here's the mystery. Most are invisible. Without a nearby star to light them, rogue planets are almost undetectable by conventional telescopes. They don't shine, they don't reflect, they drift through darkness, and yet they may not be dead. Some could still hold heat trapped inside from formation or generated by radioactive decay. A thick atmosphere rich in hydrogen could insulate the core for billions of years. In theory, lakes could form, maybe even subsurface oceans. You might picture one now, a planet the size of Earth, or maybe larger, covered in ice but warm below. No day or night, only eternal twilight, lit not by a sun but by its own breath. Could life exist in such places? It's possible. Not the kind of life that thrives on photosynthesis, but life adapted to chemical gradients, heat and pressure, deep oceans wrapped in darkness. On Earth we find extremophiles living deep underground, far from sunlight, feeding on minerals, generating their own warmth. If it can happen here, why not there? And this expands our search in a profound way. For centuries we've pointed our telescopes towards stars, searching for planets bathed in light, but perhaps some of the most fascinating worlds have already slipped past, unseen, unlit, and unreachable. Still, they remind us that light is not a requirement for mystery. Sometimes silence holds the deeper secrets. You might imagine now the journey of one such planet, ejected long ago from its home system. It moves now through empty space, no star ahead, no star behind, just slow momentum. Gravity's long exhale. It may pass near another star eventually, perhaps be caught again, perhaps not. In the meantime, it listens, it cools, it waits, and it carries its history, its minerals, its crust, its core, like a locked journal. We may never read it, but knowing it's there changes something in us. Because the universe is not just stars and light, it is worlds, some warm, some cold, some tethered, some free, and each of them tells us that existence doesn't always follow the pattern we expect. Not all families stay together. Not all dancers remain near the flame. Some step into the shadows. And even there, life, however faint, might whisper its quiet truth. We listen, and listen, and listen. Across the skies, through radio telescopes and laser arrays, through the hush of deep space, we stretch our ears for signals, but the stars keep their secrets. The universe, for all its motion and light, is overwhelmingly silent, and that silence poses one of the deepest, most haunting questions we've ever asked. Where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, if intelligent life is common in the universe, why haven't we heard from anyone? We've scanned the skies for decades, sent signals, launched golden records into interstellar space, pointed radio dishes at distant stars waiting for a pattern, a pulse, a ping. But so far, we've heard nothing conclusive. And that silence is loud. You might imagine yourself now, standing on a beach at night, calling softly across the water. Your voice echoes, but no answer comes. The waves roll in. The sky is vast, and somewhere beyond the horizon, others may be listening too, or they may not be there at all. Astrophysicists still debate how to interpret this silence. Maybe intelligent life is rare. Maybe it tends to destroy itself before reaching the stars. Or perhaps civilizations rise and fall so quickly. Their signals never overlap in time. Or maybe we simply don't know how to listen properly. One lesser-known theory suggests that advanced civilizations might communicate using methods we haven't invented yet. Quantum entanglement, gravitational waves, or other dimensions of physics we haven't tapped into. In that case, we wouldn't hear them with radio waves. We'd be waiting on the wrong frequency, like tuning an AM dial for a satellite transmission. And then there are the fast radio bursts. FRBs are mysterious signals, millisecond-long pulses of radio energy coming from distant galaxies. First discovered in 2007, they've puzzled astronomers ever since. Some repeat, some don't. Some come from magnetars, others from unknown origins. Could they be artificial? Most scientists lean toward natural explanations, but some keep an open mind. Because in a cosmos this vast with billions of galaxies and trillions of planets, the absence of evidence is not evidence of absence. And still, the paradox lingers. Are we early, or very, very late? Perhaps we're surrounded by intelligent life, but it is too different for us to recognize. Perhaps the signals are there, hidden in cosmic background noise, encrypted in ways we haven't imagined. Or perhaps we're alone, and if that's true, if Earth is the only cradle of consciousness in a silent universe, it does not make us special. It makes us responsible. Responsible for listening, responsible for continuing, responsible for remembering. But even if we never find anyone, the search itself has value. It reminds us to look, to wonder, to reach. And the silence we encounter is not empty. It is filled with possibility. You might imagine now a great radio dish, like the ones at Arecibo or Greenbank, tilted skyward in the dark. It doesn't move quickly, it doesn't hum, it waits, and above it, stars turn slowly. Galaxies shift on ancient tracks, time expands, and somewhere, in all that motion, a signal might one day emerge. Not loud, not dramatic, just a gentle hello, or a shared silence. Because sometimes, the greatest connection is knowing someone else is listening too. Whether or not we hear them, we continue the quiet vigil. Not because we expect answers, but because we believe the question is worth asking, and in asking we join a lineage of watchers, stretching from early humans who looked up at the sky with bare eyes, to modern astronomers with mirror arrays and algorithms. We are all part of the same question, and so, even in silence we listen, and we hope. Between the galaxies, beyond the bright arms and glowing cores, past the spiral patterns and the soft halos, there is something even quieter, not quite empty, but nearly invisible. It's called the intergalactic medium. It fills the space between galactic clusters like an unseen ocean, tenuous, vast and largely forgotten. It is not as thick as the clouds of a nebula, nor as dense as a solar wind. It is a whisper of matter stretched across unfathomable distances. You might picture it as the breath between stars, not full of planets, not rich with stars, but threaded with ions, plasma, and the remnants of ancient events. The intergalactic medium, often shortened to IgM, is composed mainly of hydrogen and helium in a highly ionized state. That means it's stripped of its electrons, heated to millions of degrees, yet so sparse that a single cubic meter may contain just a few atoms. Sparse, but not empty. One lesser-known detail. Despite being nearly impossible to see, the IgM contains the majority of the universe's normal matter, what scientists call baryonic matter. Not dark matter, not dark energy, but the stuff that makes up stars, planets, and people. It's just not where we expected it to be. Astrophysicists still debate how to trace this missing matter. Some of it was discovered only recently, using a technique called the Sunyaev-Zeldovich effect. In this method, astronomers observe how cosmic microwave background photons are slightly altered when passing through the hot gas of the IGM, tiny shifts that reveal otherwise invisible threads. We now believe that galaxies are connected by faint filaments of gas and plasma, stretching like tendrils across the cosmic web. These filaments act as highways for material, channels through which galaxies grow, merge, and interact. And yet, if you were floating in the intergalactic medium, you wouldn't know it. There would be no stars nearby. No planets. No heat you could feel. Just a soft, ever-present glow of X-ray and ultraviolet radiation. Diffuse, quiet, and ancient. You might imagine this region now, not as a void, but as a shimmer, a gentle haze, barely brighter than the nothingness around it, stretching for millions of light years between galaxies. We once assumed that galaxies were isolated islands, but now we see that they are more like cities connected by back roads, silent and invisible but essential. The IGM is where much of the action happens over cosmic timescales. As galaxies form and merge, they pull in matter from these filaments. They also lose gas back into the medium through supernovae and galactic winds. It's a constant give and take, a slow conversation across space, and while the IGM poses no danger to us, it does challenge our imagination, because it reminds us that visibility is not the same as presence, that brightness is not the only clue to existence. There is mass, there is structure, there is heat. But it all lies just below perception, and sometimes, when astronomers observe distant quasars, those luminous beacons powered by feeding black holes, they notice something subtle. The light from the quasar dims just a little as it passes through the IGM, not all at once, but in a pattern, like a curtain made of mist softening the light. Those dimmings tell us something. They map the medium, they whisper its shape, and through them we begin to see a different kind of universe. Not a stage filled with actors, but a stage that moves, that breathes, that connects. The intergalactic medium doesn't pulse or roar, but it holds galaxies in its threads. It is the quiet in between, and in that quiet things grow. Let's drift now toward the edge, not of space, but of something even more abstract. The edge of space. That isn't really an edge. Because in all our wondering, one question continues to echo. Does the universe end? It's a natural thought. We're used to edges, cliffs, horizons, shorelines. Even the sky appears to curve downward from our view on Earth. But when it comes to the cosmos, the rules change. The current leading models suggest that the universe is finite, but without boundaries, like the surface of a sphere, but in more dimensions. You can travel in one direction forever, never looping back and never hitting a wall. It sounds strange because we live in 3 spatial dimensions, but in cosmology, we often think of space as curved, not by walls, but by geometry. A lesser-known example: if you walk in a straight line on Earth, eventually you return to where you started. That's a property of a closed surface. Now imagine space itself behaving similarly, without ever repeating. No centre, no edge, just boundless continuity. This concept comes from general relativity. The shape of the universe is governed by its total energy content: matter, dark energy. If there's enough mass, space curves inward. If there's too little, it curves outward. If the balance is perfect, space is flat. Astrophysicists still debate which of these shapes describes reality. Observations from satellites like WMAP and Planck suggest the universe is very close to flat, but with margins small enough that a gentle curve could still be hiding in the data. So we may live in a universe that is finite in volume, but has no boundary. Not an endless hallway. more like an ever-expanding fabric that never frays at the edge, because there is no edge. You might imagine this now, not as a void with a border, but as a soft unfolding, a kind of cosmic breath that continues in all directions, never reaching a stopping point. This is why, when we speak of the edge of the universe, what we usually mean is the edge of the observable universe, the farthest distance light has travelled to reach us since the beginning of time. Currently, that edge is about 46 billion light-years away in all directions. Beyond it, we don't know. Light from there hasn't reached us yet, and perhaps never will. But if the universe is infinite, or even just unbounded, then there is no special spot where it ends. No sign that says, "Here be dragons," just more of the same. And this has a curious consequence. Wherever you are, you're at the centre of your observable universe. So is every galaxy, every star, every drifting planet. Each one sits in the middle of a bubble of light, the visible sphere that time has allowed them to see. It's not arrogance, it's geometry, and it reminds us that the cosmos doesn't revolve around any one place. Not Earth, not the Sun, not even the brightest galaxy. It simply expands, quietly, unhurried. And in that expansion, space itself grows, not into something, but out of itself. It's a hard idea to hold, but a beautiful one. You might close your eyes and imagine standing at the edge of the universe. You expect a wall. But instead, you find more space, more time, more stars, or perhaps not even that, just more geometry, more room for things to continue becoming. And so, the universe doesn't need walls, it doesn't need ends, it only needs the gentle logic of its own expansion, and the quiet courage of us trying to understand it. Let's pause now in the most colourful places in the universe, not bright like a star, not sharp like a planet, but glowing gently, breathing with heat and chemistry. We drift into a nebula, cloud of dust and gas so vast it could swallow hundreds of solar systems, yet so diffuse you could fly through it without knowing. These aren't just beautiful sights in telescope images, they are cosmic laboratories, regions where elements mix, stars are born, and molecules begin to dream of life. You might picture the Orion Nebula just over 300 light-years from Earth. It glows softly in visible light, roses and violets and golds, carved by newborn stars emitting strong winds and ultraviolet radiation. But it also hums in infrared, millimeter waves, and X-rays, each revealing a different layer of its story. Here, atoms are joining, breaking, reforming. It's not chaos, it's chemistry. Nebulae like Orion, or the Eagle Nebula, or the Horsehead, or the Pillars of Creation, are regions dense enough for gravity to begin its slow work. Hydrogen atom clump together, forming molecules. Molecules gather into filaments, and eventually under the right conditions those filaments collapse. A star is born. A lesser-known detail, some nebulae are so rich in complex molecules, carbon chains, alcohols, even amino acid precursors, that they may have sown the seeds of life across the galaxy. These molecules can cling to icy grains of dust, ride comets or asteroids, and survive the harsh journey to planetary surfaces. This is called panspermia, the idea that the building blocks of life might be spread by the cosmos itself, drifting slowly across space on tiny carriers. Astrophysicists still debate the likelihood, but what we do know is that the raw materials are common. Organic chemistry is not rare, it's woven into the clouds. You might imagine now a region of space lit not by starlight, but by the gentle fluorescence of ionized gas, hydrogen pinks, oxygen greens, sulfur reds. A young star cluster glows at its heart, while tendrils of dust stretch outward like arms, shaping the flow of the gas, shielding pockets where new stars are quietly taking shape. These cradles are not static. Nebulae live on the scale of millions of years. Winds from young stars carve cavities. Supernovae inject shockwaves. New generations of stars trigger fresh waves of collapse. It is a cycle: birth, light, collapse, dust, and again. And through this cycle, chemistry evolves. Simple atoms like hydrogen and helium were made in the Big Bang, but everything else, carbon, nitrogen, oxygen, iron, gold, was made inside stars, then scattered by explosions. Those elements mixed into nebulae, where they joined into molecules, and in some cases those molecules became the backbone of cells. This is the slow alchemy of space. You might imagine floating now through the Lupus 3 cloud, or the Taurus molecular region, dark, hidden in visible light but glowing brightly in the infrared. Here, interstellar chemistry plays out in silence. No bubbling pots, no laboratories, just patience, temperature, and time. Could it be that, somewhere in these dusty folds, molecules are arranging themselves in ways we've only seen on Earth? Self-replicating patterns, protoproteins, chemical pathways not yet alive, but not quite inert. Maybe, maybe not, but the possibility is enough. Enough to guide our telescopes, enough to guide our questions, and in asking, we become part of the chemistry ourselves. We send spacecraft to comets and asteroids, scraping dust from ancient surfaces. We analyse interstellar grains caught in collectors, looking for hints of sugars, acids, or structure. We scan nebulae with radio telescopes tuned not to voices, but to vibrations of carbon chains, and we find them, not life, but its whispers, the quiet hints that the universe knows how to build the pieces. What happens next depends on where they land and how long they wait. In all our wandering, all our drifting through time and space, a quiet question begins to form, one that echoes not from the sky, but from within us. Why now? Why do we find ourselves here, at this moment, able to look outward with such clarity and inward with such curiosity? Are we early or very, very late? The universe is nearly 14 billion years old. Our solar system formed only 4.6 billion years ago, and human civilization has existed for barely a blink, just a few thousand years of recorded memory. And yet, here we are, mapping galaxies, measuring redshifts, catching gravitational waves, and pondering exoplanets. You might feel the strangeness of that now, as if waking up in the middle of a grand performance with no idea when the show began, or how long it might still run. Astrophysicists still debate the timing. Some suggest we are early in cosmic terms, that the best is yet to come, that new stars will continue to form for trillions of years. Others argue the opposite, that we arrive during a rare golden window, when stars are still plentiful, metals abundant, and the universe transparent enough for us to see its beginning. It's a gentle tension, too early to witness the end, too late to witness the beginning, yet perfectly placed to observe both. A lesser-known idea in this debate is something called the cosmic coincidence problem. It refers to the surprising fact that dark energy, a mysterious force accelerating the universe's expansion, is only now becoming dominant. For billions of years, matter governed the cosmos. But just in our era, the balance is shifting. It feels timed. But perhaps it only feels that way because we're here to notice it. This leads to what's known as the anthropic principle, the idea that we observe a universe compatible with our existence because, well, otherwise we wouldn't be here to observe it. It's not a satisfying answer, but it's a humbling one. We don't know whether intelligent life will arise again elsewhere at another time. We don't know whether consciousness blooms only under rare conditions, like a flower that needs just the right warmth and just the right rain. But we do know this. Right now the universe is knowable. Stars still shine. Light still travels. Background radiation still reaches our instruments. And if we waited too long, say, 1 trillion years, cosmic expansion might stretch the light so far that nothing remains visible. Other galaxies would slip past our event horizon. The cosmic microwave background would fade into undetectable wavelengths. A future intelligence might live in a galaxy so isolated, so starved of external clues, that it could never know the broader universe existed at all. They might see only blackness beyond their own stars. They might think theirs is the only galaxy. And they would be wrong. Just as not long ago we believed our own galaxy was the whole of everything. So maybe this is the perfect time to be curious, to ask, to map, to wonder. Maybe this is the universe's brief moment of self-awareness, when stardust arranged into thinking forms begins to understand the stars. You might imagine now our planet from above, a tiny world. A flash of green and blue, circling a modest star in an unremarkable corner of a spiral arm, and yet it listens, it remembers, it dreams. We are not the centre, we are not the purpose, but we are here. And that, in a universe that offers no guarantees, is something miraculous in its own quiet way. So whether we are early or late, the truth remains. We are part of the story. And tonight, as we drift through its pages, we remember that awareness is not a given, it is a gift. And now, at the quiet edge of our journey, we return to where we began. Not with Three-Eye Atlas, the object that caught our eye, but with a different kind of mystery, the one we almost missed. Because while our gaze was fixed on that flickering visitor from another star, brief, harmless and gone, the deeper question was forming just beneath the surface. What else have we forgotten to see? You might recall how Three-Eye Atlas stirred attention. It entered our solar system with a whisper, not a roar. It moved fast but left no damage, no trail of warning. It wasn't a threat and yet it captured headlines. Why? Because it was visible. But as we've seen across this journey through starlight and silence, visibility is not the same as danger. In fact, the most profound forces shaping our universe, the dark matter scaffolding, the gravity waves, the intergalactic plasma, the rogue planets and black holes, they do their work unseen. They do not flicker. They do not crash. They drift. They hum. They endure. The real threat, if there is one, may not come from a fast-moving object or a violent event. It may not arrive with noise or drama. It may not come at all. Instead, it may already be here. It may be the slow forgetting, the gradual loss of wonder. The quiet turning away from the sky. You see, the universe is not just a place, it's a mirror. When we look out, we also look inward. Every question about stardust is a question about origin. Every theory of time is a theory of meaning. Every faint galaxy at the edge of visibility is also a reminder of how fleeting and beautiful attention can be. We don't explore space only to protect ourselves. We explore because curiosity is the most human thing we do. Because asking, what is that, leads us to answers not only about comets and gravity, but about ourselves. One lesser-known observation from decades of sky watching is how easy it is to stop noticing. Cities grow brighter, skies grow hazier, fewer people look up at night, and with each passing year, the visible sky shrinks. We lose not the stars themselves, but our connection to them. Astrophysicists still debate the practical threats of solar flares, gamma-ray bursts, rogue objects, and those questions matter. They're worth studying. But the quietest danger, it might be ceasing to care, because wonder is fragile. And if we let it go, if we stop listening, stop looking, stop feeling humbled by the scale of the sky, we lose more than knowledge. We lose perspective. You might imagine now standing beneath a clear sky, no city lights, no rush, just the velvet dome of stars above. You look up, you exhale, and for a moment you remember how small you are, and how vast it all is. That is the real gift of astronomy. Not predictions, not defense systems, but perspective. So let the harmless objects pass. Let the skies stay open. Let the questions remain unanswered, because some of them should be. We don't need to solve everything. We just need to keep asking, to keep looking, to keep wondering. Because maybe the real threat isn't out there at all. Maybe it's forgetting that the universe was never silent. We just stopped listening. And now the stars grow quieter. The sky softens. The journey slows. We've drifted through galaxies and between invisible threads of gravity. We've listened to waves we cannot feel and followed light older than memory. We've imagined rogue planets sailing without suns, oceans sleeping beneath layers of ice, and nebulae humming with slow chemistry. And through it all, a quiet truth has emerged. This universe, vast and old, is not in a hurry. Its rhythms unfold on scales far beyond our own. Its stories are written in starlight, in dust, in long silences, and yet here we are, brief moments of awareness in the slow pulse of deep time. As you settle now, let yourself remember the gentleness of cosmic drift. Let your breath follow the rhythm of orbiting moons. Let your thoughts move like photons across quiet expanses. Let your mind become weightless, like dust in a nebula, floating through ancient light. There is no urgency here, just the hush of a universe still unfolding, still building, still breathing. And as you drift off to sleep, know that you are part of this rhythm. Your atoms forged in stars, your thoughts rising like signals into the quiet dark. You are a witness to the infinite, a small, luminous thread in the tapestry of space. So close your eyes now. Let the starlight fade. Let the questions dissolve into dream. There is time. There is silence. There is wonder. And somewhere, out beyond the visible, ancient light continues its slow journey, still arriving, still whispering, still here.